Good morning. Very sorry for the delay. It's continue from where we left off yesterday. As we discussed, we have three levels of any structural analysis when you're looking at flight vehicle structures, especially those made out of composites. So we started from the lowest length scale, which is micromechanics. So we'll have a few more, couple of slides more to discuss this, and then we will get on to mesomechanics, which is the interface between the micromechanics that we'll study now and the macromechanics for the structure as a whole. Okay, so just to refresh, we talked about the simplest model, the rule of mixtures, and we did the derivation for the longitudinal modulus of the composite in terms of the longitudinal modulus for the fiber and the longitudinal modulus for the matrix, the matrix being isotropic. So it's the Young's modulus of the matrix in any direction for that matter. So we introduced the concepts of the volume fraction. We saw that something familiar from what we have done for densities and various other things. Then I wanted you to derive as the first part of the fourth homework the Poisson's ratio, which has a very, very similar kind of a behavior. Now, if you look at it, this is something that you would be also familiar from a set of springs. So either you have a couple of springs in parallel, in which case you have, let's say, the spring constant K1 and K2, and you try to pull this apart with a force F. Then it's the force that gets divided into two parts, namely F1 and F2, whereas this particular rod is kept, let's say, on rollers and it's being pulled, so it remains vertical, this particular plate or clamp which is connecting the two springs, and then when you're trying to pull that apart, you know that this what we are talking about is something that happens. So very, very, very similar to that. On the other hand, there is also a situation where instead of being in parallel, these same springs can be in series. So this is the same K1 here and K2. Instead of connecting them in parallel, we have now connected them in series, and now we pull this with the same force F. Now you see that the force is not getting divided, it's the same force acting through both. Okay, so if I were to draw the free body diagram of K2, for example, it would be F on both sides. Similarly, if I were to draw the free body diagram of K1, it would be F on both sides, right? So what was getting divided there remains the same over here, but what remained same there was the change in length. Okay, the change in length for both the springs was one and the same, because of which the strain remained one and the same. Okay, so problems like these are called as isostrain. What it means is that the strain is a constancy and we take advantage of that. Whereas a problem like this is isostress. Okay. Now these parlances of course come from structural mechanics, deformable bodies, etc., strain and stress. But whether it is a set of springs or for that matter even in of course the opposite happens in the case of the dashpot. So if you have, let's say, a viscous damper, or what's referred to a dashpot, then you will see that the exact opposite happens. When it's parallel, the set of dampers, which you typically denote by something like this. So there you will have, in this case, isostress, and in this case, isostrain kind of behavior. In other words, what happens here is pretty much like a proportionality factor that you're taking the proportionality with respect to the corresponding properties of the constituents, and the weighting factor there being the volume fractions. Now, what happens in a situation like this is you continue to have the same contributions, but now it is in a reciprocal sense. So, for example, instead of the longitudinal modulus, if you were to be talking about the transverse modulus, then that would be having a behavior like this. And some of you familiar with, let's say, LCR circuits, which involve in electricity the inductors, capacitors, etc., the resistors. So then there also you will see the inductance and the capacitance have this kind of dual behavior, just like springs and dashpots do in mechanics. So there's a lot of parallel analogies in various branches of physics that you can actually, if you understand one very clearly, you can apply those analogies in order to understand something else much better, right? Now, if you were to, let's say, take a curve like this and plot versus the volume fraction of the fiber, small vf, that we are talking about over here, obviously it can take on the value from 0, which means there's only matrix, and then you have 1, which is just the fiber alone. Okay, so here you have matrix alone, no fibers, and here you have fibers alone, right? And here if you plot the Young's modulus of the composite in the longitudinal direction, I'll just call it E, because we'll plot on the same set of axis, we'll plot ET as well, that is the transverse modulus of the composite. Then you see that when it's matrix alone, obviously the value of that is same as the Young's modulus of the matrix, which anyway is also part of the equation that you see over here, right? And it's isotropic, therefore we're not giving the subscript L. On the other hand, once it becomes fiber alone, it becomes a much larger value, which we call as the EL of the fiber. Okay, not all fibers are anisotropic. There are quite a few fibers which are isotropic as well, but nonetheless, even when you use an isotropic matrix with an isotropic fiber, you will end up with a anisotropic composite. So that's important to remember, just because of the fiber geometry, right? Now you see this particular thing at this point, you know that it's because just the fiber. This is also a point on that, but yeah.
So what does the L again stand for? Because
Yeah.
for
Yeah.
the matrix you have just
Right, right. So let me just resketch that unit cell that we were talking about.
Oh, so like along the line.
Exactly, exactly. So now you're having an axis like this, which is x1, along which the length is there. So it's essentially the longer dimension, which we call as, just like the same starting 4 letters, longitudinal. And therefore we take this L as the abbreviation, and that's what you see as the subscripts in all the variables that we have introduced. Okay, whether it is in this or the next thing that we are going to deal with. Okay, so anything which is in the shorter dimensions, so in this case we have 2 shorter dimensions because it's a beam-like problem. Okay, starting from the center of the fiber actually. So these are called as transverse directions. Okay, so this is T, standing for transverse. Now the kind of symmetry that this problem has, whether it is the x2 direction or x3 direction, both are smaller dimensions compared to the x1 direction. So in fact x3 is also a transverse direction. So it's not only x2 but x3 is also a transverse direction. So both of these are transverse directions, and to distinguish the two we will refer to this as t prime. Okay, so just to make sure that we are talking of two different directions there, x2 and x3, we will call one as t and the other as t prime, but essentially both are transverse directions. So the overall qualitative behavior will be very similar in either one of those directions because both are perpendicular to the fiber direction. Okay, it's just in the fiber direction we've always been saying the main advantage of the fiber, the geometry we saw in the last class, is that its superior properties, mechanical properties of stiffness and strength along the fiber direction. Any direction perpendicular to that, it's very weak, it's very flexible, and therefore the ET prime, which will be equal to each other, will be much smaller compared to EL, which is the longitudinal modulus that we are talking about now, right? So now, how do you think we have got 2 points over here? One is on the x-axis we have 0, and on the y-axis we have EM. So 0 comma EM is one of the points that we have here, and we have one more point here which is on the x-axis 1 and on the y-axis ELF, right? So how do you think the curve joining these two should be? Exponential? Which of these two? Top one, okay. So anybody else? So what we are plotting is EL, the Young's modulus in the longitudinal direction for the composite, right? So when the volume fraction of the fiber, I think that's the maximum I can go there. It's okay for you?
Yeah.
This way? Yeah. So right now we are plotting EL, okay? I want to plot everything for the composite, so ELC, right? Even if I don't write C, it means the composite, okay? So that's the default. No, when it's fibers alone, it's this point, okay? Because volume fraction becomes 1 and the value is known, ELF, right? Similarly, when there is matrix alone, the volume fraction of the fiber becomes 0, right? So you think that's the right one? Yeah, okay. What about Nafis and Matt?
I think it might be linear. We use the equation.
Right.
All we're doing is increasing volume fraction for fibers.
Yeah,
so
yeah.
When we increase by that much, decrease by whatever change we're doing for the decrease of volume fraction of the matrix.
Right, right. So note that all that we are doing is plotting EL versus VF, right? So now this is a constant. So obviously this is linear. Now we have to check the second term. This is also constant. But VM, we showed you there is no additive. It just becomes 1 minus VF, right? So the 1 will give a constant term, and then which is what gives you your intercept on the y-axis, right? And then you have a minus VF times EM. So the slope will be ELF minus EM, right? So it will be a straight line as Nafis pointed out, right? So this is the actual line that you would have.
And also, will it differentiate in a way because of the real world?
Differentiate between the real world and this equation, you mean?
Yeah.
Yeah.
Because, yeah.
No, yes. See, this is, as I said right up front, this is the simplest model that you can have, right? So the simplest model is a linear model, but it so happens that when you do experimental tests, this is reasonably good enough, okay? So you do not find too much of a discrepancy from there. Maybe because there is some uncertainty in these properties like ELF and EM, you don't know for sure. there can be a certain probability density distribution function for those. So therefore, because of that, there can be a variation of EL. But if you know ELF and EM exactly, and also the volume fractions, because the volume fractions, again, measurement is a little tricky how you actually do it. One, of course, during the manufacturing process itself, you know how many fibers you're probably going to put. You can estimate that because the number of toes that you have, and each toe how many fibers it has, and then you know the volume of the matrix that you're going to use. So from that you can estimate. Or if it's an already existing composite, how typically people do it is a destructive test. They burn it because the polymer will reduce to ashes. Most of these fibers will remain as they are. So then you actually weigh that and use the density of those materials in order to arrive at the estimate for the volume fractions. So more or less, this is a reasonably well established thing. The reason is that the isostrain model that is there is a much more rigorous model compared to the isostress, as we shall shortly see. It's kind of dicey. Okay, so you get typically ballpark values but not exact values. So what Ivan you're saying will apply for the next thing that we are going to do, where yes, the real life will be very different from what we will see as an equation. Okay, so first of all, what we will see as an equation, before even we derive that, let me put it very simply, because rewriting that first equation first of all is just EL equal to ELF. Let me write the second term with the EM alone. So EM plus ELF minus EM times VF. Okay, so you clearly see that all that I've done is to replace VM as 1 minus VF, as I just discussed, and therefore having everything in terms of VF alone, one volume fraction. Okay, again, when you're talking of reality, as Ivan mentioned, you will not have only two constituents in the composite. Usually you'll have a few additives in order to enhance some of the properties or to bring in additional new properties which are not existing with the fiber and the matrix alone, and therefore you will see that you could have changes because of that. Okay, but essentially, as long as there are only two components, the fiber and the matrix, and then you know all these properties reasonably well, then you just end up with a straight line. Okay, so now that's the equation for the isostrain model, which is typically given credit to Voigt, and usually gives you an upper limit. Okay, on the other hand, when you go to an isostress kind of a model, the credit, there are of course many people who have worked on it, but traditionally the credit is given to Royce, and it's usually the lower limit. So truly speaking, the ET that we are going to derive for the transverse direction, or for that matter ET prime, both are going to be the same. So the transverse direction property for the Young's modulus is of the composite is going to have a behavior like this, and that's not going to be accurate enough. So it will only give you qualitative values. You cannot be sure of its accuracy, because in reality it will be slightly different. Okay, now this is an example where we are saying that the EL of the fiber may not be equal to ET of the fiber, but there are many fiber examples like glass fiber, for example, where you will have whether it's ELF or ETF, it is the same. So if we take an example like that, then the points still remain the same even for the second example. It's only that the curve is going to change, okay, because the equation is going to change. Here we had a linear equation with a slope and a y-intercept. Y-intercept was EM, the slope was ELF minus EM, and once we put that, you end up with this this particular curve, which is a straight line. Okay. On the other hand, when you're deriving ET, which we will do shortly, the end result will be Et is equal to, again for the composite, so I'm not putting C explicitly as a subscript because it's understood, will be, okay, let me put it in a way that is more clear to observe. One divided by Et is equal to nu F divided by ETF plus nu M, or not nu, because nu I'm using for the Poisson's ratio. Let me write it as small v, so just to be consistent, not confused with the new variables that you're coming across. So this is small vf and small vm by Young's modulus of the matrix, which you are assuming to be isotropic. As I said, in many fiber examples also, including the ones which are used in aerospace composites, ETF and ELF might be equal to each other, but just to keep it general, we are having the different symbols because in general they can be different, right? Now suppose we take the case where ETF and ELF are one and the same, then still you will have these two values, but now what is going to happen is, if you at this point you have Vm equal to 0, right? When the VF equal to 0, so you will have Vm equal to 1, right? So then you will have Et equal to Em. So once again you have the same point, right? On the other hand, when you take Vf equal to 1, Vm will become 0, and then therefore you will have once again the same point in case ETF and ELF are the same. So once again you start with the same 2 points, but the curve that is going to be joining them is going to be different. So how do you think that this particular curve is going to be? I'm plotting, instead of EL, I'm going to be plotting ET, because both are for the composite. Now I'm going to be plotting ET also versus the same variable, the fiber volume fraction. Okay, so again I have two endpoints. I just need to know how the curve between them is going to be. So what I'm relating is ET and VF. Now you see that no longer that linear relationship holds. Okay, it's a non-linear relationship. So one side it's on the in the denominator, here it's in the numerator that you see. Okay, so and also of course your Vm once again will be equal to 1 minus Vf. So there is a Vf dependence coming from this term as well. Okay, so now how do you think the line joining these two is going to be? Is it going to be something like this, or something totally different from either one of these? So from this equation, can you see you're just plotting? You can think of this as the variable y, this as the variable x, everything else is constant. Okay, the ETF, EM are all constants. So we have only two variables in this problem. One is a dependent variable ET, okay, and the independent variable VF, right? So if this is the case, then how do you think this variation is going to be? What happens if VF starts increasing? Does ET increase or decrease? How rapidly it increases or decreases? Yeah, okay. Anybody else? You think Matt has got it right, or you think differently? Any reasons, Matt, for the choice?
Like if you just look at like the VF terms, like the first like as you increase VF, like the first term would increase, then of course the second term is decrease. But since it starts with 1 minus at first, it would be still positive, but as VF increases too much, the second term would be negative.
So let's probably look at it as two terms over here. Okay, so this same thing I can write it instead of this as, because there is 1 minus Vf, both are divided by Em, so I can write it as okay. So then I can put the constant terms separately, 1 by Em, and then I can add Vf times 1 by ETF minus 1 by EM. Okay, now you have, what do you see on the right hand side? Is the right hand side a linear or a non-linear function of VF? Remember, all the E's, whether it is of the matrix or the fiber, are constants. Okay, so they are not varying. It's only the volume fraction of the fiber that we are varying. Still linear. Okay, so you have a constant term, you have a proportional term, right? So just like there also you had a constant term, you had a proportional term. So the right hand side is still a linear portion. So is the line the same, exactly same as before?
Isn't EM now bigger?
EM is not bigger, but what you're right is 1 by EM is bigger, right? Because yeah.
So are we plotting 1 over ET or?
No,
just-
no. I'm plotting the modulus because that's what I'm interested in, right? So I'm just like I plotted EL, I'm plotting ET, not 1 over ET. So now,
So it's ET equals 1 over EM.
yeah. You can think of this as just some constant C naught. You can think of this constant as some C1. Okay, so it's C naught plus VF C1. So Z1 rightly pointed out, we are not plotting 1 by ET. If we were plotting 1 by ET, yes, you end up with a very similar straight line because the 2 points are the same, you're just connecting them. But of course, also assuming that ETF and ELF are the same, okay, which is the case for most fibers anyway, right? But since you're plotting the reciprocal of the left hand side, it's no longer linear, okay? So this right hand side as it is linear, but once you take its reciprocal, it no longer remains a linear plot, okay? So it's going to be some kind of a reciprocal behavior, but there is also a constant term, okay? So if it was just this term alone, then you know how it will be, just a reciprocal term how to plot. But now you have that as well. So you'll have a tendency which is something similar to that. So what will actually happen is you will have a curve like this. In fact, it will be much more because of the relative values of EM and ETF that he was pointing out, Ivan was pointing out. So this curve will actually be something like this. Okay, so this is how it will kind of increase ET with VF, right? So it is monotonously increasing, but the rate of increase at lower values of VF is much smaller, so almost like a constant, okay? Very, very small increases there, and then suddenly it shoots up when it goes close to VF equal to 1, then it has to reach that value of ETF, so it goes there. So in other words, it's kind of matrix dominated property. And this is the case with most transverse properties. So whenever you're talking of transverse properties, remember that, yes, to get it accurately, we have to put both, we have to take the volume fractions and try to find out. We may not actually use in real life simple models like this. You have to go for a little more complex models beyond the scope of this course. But nonetheless, you will get reasonably good values if always remember that the longitudinal direction properties, whatever properties you're dealing with, are mostly dominated by the fiber properties. If you know the fiber property, the first guess can be almost the fiber property is slightly lesser than that because the matrix is inferior, and therefore the mixtures properties will be slightly inferior compared to the fiber, but not by a whole lot. On the other hand, any property you're trying to get in the transverse direction, it will be usually matrix dominated, okay? There can be exceptions, but I'm just saying this is the general thumb rule that will get you right most of the time, right? So that's why you see that it's almost the same as the matrix property, only slightly towards the end it actually increases, okay? So that's the this particular equation, but of course like we derived EL, we have not yet derived ET. we can do that very simply, because that's essentially the isostress problem. And in this case, you know that if I'm pulling it by a force F, what happens is not F getting divided into F1 and F2. As I said, if you draw the free body diagram of the spring, the second spring, it will have F on both sides. Similarly, if I draw the free body diagram of the first spring, it will also have F on both sides. So there will be a delta 1 and there will be a delta 2. And those delta 1 and delta 2 is what gets added up to give the total delta change in length. Okay. So delta L1, delta L1, delta L2, the change in lengths, and delta L1 plus delta L2 will give you the total delta L that is there, and that's what you will then use in order to get to the equation for ET over here. Is this, you see where we are heading? Yeah.
So,
Oh, yeah.
since we divide by VF, right, to get ET in the end,
Mm-hmm.
and if VF is really small, it means the term itself will get big.
True,
Is it?
true. Yeah, yeah.
So I'm not sure that.
How this plot is looking like this? Okay, you just take some numbers and see for yourself and actually do a plot of that. So you can take, to start with, let's say the more crudest approximation you can have is EM is 0, right? So what happens if EM is 0, because it's negligible compared to ETF? So then what do you think happens? So you're essentially putting your EM equal to 0, right? So what happens when you're trying to take it in the reciprocal sense? So just try to play around with that. Okay, so then you will see the trend that happens.
So I guess like the VF relationship doesn't affect that much.
Right, exactly, yeah. Okay. So it's all because of the coefficients that are there. There's a huge difference between them, so there's a domination of one over the other. Okay, so here on the other hand, you see once again the same thing holds, that ELF is very large compared to EM, so it's the second term which hardly contributes. Okay, so if I take EL as approximately equal to ELF itself, or ELF times VF rather, so then that would be the dominant term there. Okay, in that straight line, I would get a very small difference. Maybe I will get a line like this. If I drop off the second term in this particular equation, I have only the first. Of course, it will go from 0, right? So it has to go to the same point, but it starts from essentially 0, right? If I drop off the second term, it is just EL equal to ELF times VF. So that's, you see that even when I have no matrix at all, so essentially it's essentially becoming like that. Whatever, or rather the matrix properties are so inferior that the Young's modulus of the matrix is almost 0, negligible, so you just neglect it. Then this is the straight line that you'd get, which is not very far off from this. Yes, close to the value of VF equal to 0, there is a difference, but otherwise for most of the distance you see hardly any difference compared to the large value that you already have, right? So on the other, so that's what I was saying, that longitudinal properties like EL are dominated by the fiber, whereas opposite happens, the domination by the matrix for the transverse properties. Yeah, have I addressed that, Ivan? You're still not convinced? Yeah, it's better for you to take some numbers and do a plot, then you'll see the typical trend of the curve will be like that. Yeah. So let's go ahead with the derivation. Any other questions on this? Anybody? No? So we will take a model which is very similar to what we did last time. So essentially we are talking about two components in this mixture. One is the fiber, which will denote with subscript small f, and the other is the matrix, which will denote with the lowercase m, right? The only difference from yesterday's derivation that I was doing is that I was applying the force this way in order to get the EL, because that's the longitudinal direction, the direction x1. Okay, so this is the direction x1, this is x2, and this is x3, right? Now, in the parlance that we have been using, this is nothing but L, this is T, and this is T prime, another transverse direction, just distinguishing it, right? So now, instead of applying a force along x1, which we called as F1, we are applying a force along x2, which we will call as F2. Okay. Now I can very easily draw the free body diagrams of these. So once again, I assume a perfect bonding. So if I have F2 here in the matrix, I have F2 here as well, right? Similarly, for the other one, we have F2 and we have F2 here. This is the fiber, right? So it's kind of clear that whatever you're applying is not getting divided, it remains the constant, okay? Because that's the only situation under which this can be under static equilibrium, right? And it is under static equilibrium, okay? No other forces coming into picture, so there has to be a balance between the force on the top and the bottom, which is what we have indicated over here, okay? So now this is the case, then we can see that what is actually getting added up are the deflections. So this is going to increase. Let's say we get our coordinate from here without loss of generality, that you have x3 from the interface, then there is going to be a small increase in size because of F2 of the fiber thickness, and similarly the matrix as well, right? So you started off with a certain L F and L M, and now you have a delta LF and a delta LM that is going on there, right? Now we know that the total delta that is going to be there, change in, let me not call it L because we are using L for the length, so we can call it, for example, breadth or height. The second direction we've usually been talking about the breadth, so we will put it as BM and delta BM, BF and delta BF, okay? So that's this distance, and this distance that we are talking about, right? So now we know that the total change in length that is there, that is the delta B is equal to delta BF, delta BF plus delta BM. So that's the total change in length that is happening. And what we are interested in is the strain that is occurring because of this. And so therefore you will see that there in the previous example where we are trying to pull it in this way, the change in length of both was the same and the original length was the same, so the strain remained the same, right? Here the strains are getting added up, okay? So that's essentially what is happening over here, but it's getting added up in a very, very different way, because what is actually getting added up is the change in the lengths of each one of them, right? So the change in the length is related to, of course, the strain, so and the original size of that, right? So now if I go back to that, your delta B will therefore be equal to your gamma 22 or gamma TT, whatever you want to call that. So it's in the two directions, so let's call this as gamma 22, that is your strain in the overall strain in the hypothetical material that we are talking about as the composite, which is equivalently homogenized. So this whole process is called homogenization that you're doing instead of the heterogeneous mixture that we have of fiber and matrix. We are taking the same size and we're calling it C, that is the composite. And it's of the same overall dimension, and to start with, and after you apply the load also, the change in dimension is the same as the overall change that is happening over here. So this is what we call as the equivalent homogenized model. So always remember that this is hypothetical, okay? This is not in reality. But having something like this through a process called homogenization, where you go from where you're going from this to this, so that transition that you're taking from a heterogeneous structures, this is heterogeneous, to the homogeneous or rather equivalent homogenized structure, which is hypothetical. That process is called homogenization, and it's a very, very important critical part of any analysis that you do over there. Okay, so now you have the total change in length is equal to the change in length of the or rather breadth. The change in breadth, total change in breadth is equal to the change in the breadth of the fiber and the change in the breadth of the matrix. Okay, and that change can be written in terms of the strain and the original lengths that there were. So gamma 22 of the composites, I'm not putting C explicitly because it's understood as the default. I'm just putting it as into the overall B that was having, so it's multiplying that. Okay, so now what about the change in length of the fiber? It should be equal to the gamma 22 in the fiber multiplied by the original fiber breadth, which is BF. Similarly, you will have here you will have gamma 22 in the matrix multiplied by the breadth of the matrix. Okay, so this is what we have now. So the first step is to go from what you think is getting added up, okay, which is like similar to what we did yesterday. There we said what is getting added up is the forces F1 and F2 taken by this and this when I'm pulling it this way, and then I started expressing the force in terms of the stress and then the stress in terms of the strain, and then we took advantage of the strain being equal to each other, right? So we're going to do something very similar over here, that we know that the forces are the same. So whether it's the force in the fiber or the force in the matrix, it's all one and the same, equal to the applied force F2 that is there, and therefore I have to head towards that, right? So the next step is to first I've replaced the change in breadth with the strains. Now the next step is to replace the strains with the stresses. How do I do that? I invoke the Hooke's law, right? So I can write my sigma 22 as sigma 22, right, divided by E, and the E, particular E that I'm interested in now is the transverse modulus, right, because it's in the T direction. We said x2 and T is the transverse direction because it's the smaller of the three dimensions, and same thing you will get if you do with respect to x3. We don't need to do it separately. It's the exact same result that you will get, right? Now that B continues to be there, and this is equal to, in this case, what is the strain in the fiber in the two direction, that's equal to the sigma 22. This sigma 22, remember, is in the composite, is in the equivalent homogenized thing, it's in C. Okay, when I don't put a subscript, it means it's C default. Okay, whereas here I'm going to put a subscript and I'm going to call it fiber, right? So, and it has to be divided by the Young's modulus of the fiber in the transverse direction. In the general case, that could be different from ELF, and that's of course multiplied by BF. And then I have the second term, which is also very similarly expressed in terms of the stress, this time in the matrix, divided by the Young's modulus of the matrix, which is isotropic, and therefore it's the same EM that we are familiar with. Now you bring in the last term there, product with the M, right? So now this is what we have, right? Now we can express the stress sigma 22 in terms of the force that is applied, because it's the force per unit area, right? And that force is over the same area, whether it is on the top surface or in the middle surface, on the bottom surface, everywhere it's the same, right? Because these two are perfectly bonded to each other, so they have that same area of interface that we are talking about. So instead of writing sigma 22, I can write it as the F by A, and that both F and A are the same, okay? So in other words, your stresses are all equal to each other. So sigma 22 or sigma 22F or sigma 22M, they are all one and the same, because the same force applied over the same area, not exactly same area, but the quantitative value of that area is the same. So for example, this is applied over the topmost surface, this is applied at the interface, this is applied at the bottom surface, but the value of that F is the same, the value of that area is one and the same, and therefore the stresses are the same. So I don't need to put this subscript F, it will be equal to sigma 22 itself. This will also be equal to sigma 22 itself, and then I am left with the quantities of interest ET, ETF and EM, but not in terms of volume fractions, but instead in terms of B's that we have over here. So I can rewrite that, cancelling out the sigma 22's, because all three terms have sigma 22 in the numerator. I can leave that, and then I can take the B to the right hand side. So I'm left with 1 by ET, which is what I wanted to start off with, and then that can be written as 1 by let me put it as BF by B divided by ETF plus BM by B divided by EM. Okay. Now I can multiply both the terms in the bracket in the numerator on the right hand side, numerators on the right hand side, with the length and the height, which is the same for both. Okay. So which is L and H. So L and H is the same whether it's in the fiber or the matrix, the same length, and it's the same height, which is essentially into the board, into the whiteboard. Okay. So L and H are the same. So I can multiply both by LH, which is what I'll do here. So I'll multiply this by LH, this also by LH. I'll multiply this by LH, this also by LH. Now I recognize those as nothing but the volume of the fiber and the total volume, the volume of the matrix and the total volume, right? So that's nothing but VF, and this is nothing but VM. And then we end up with the result that we wanted. We already discussed earlier. Small VF divided by ETF plus small VM divided by EM. Are the steps clear for you? Here? Yeah? Any questions, doubts? No? All good? The same thing. Yeah.
So when you multiply by LH,
Yeah.
did you say both sides?
No,
Multiply the top and
I'm
bottom.
top and bottom. So this LH cancels. Similarly, LH I can do the same LH by LH here, but that's again going to be 1, right? So it's not going to matter. Since I had only the breadth ratio, I'm just saying that the breadth ratio is same as the volume fraction here, because lengths and heights remain the same. They're not changing, right? For the fiber, for the matrix, and for the composite as well, they are one and the same, right? It's only the breadths which are different.
Because that initially are the absolute volumes and that is kind of
Right, correct.
That's why like the V's come to be.
That's right, yeah. Any other questions? No? Okay. So now the same thing can be written in this way. Then you can see that curve that we were drawing. It's more evident if you look at it from this perspective, because we were talking of on the left hand side 1 by ET. So we're taking the reciprocal of both sides. Then you get on the left hand side ET itself, which is what you have there, and then you have 1 divided by this whole thing. Then you can do an algebraic manipulation of that, and eventually this is what you would get, which is very straightforward to see, right? So this is another way of writing that reciprocal law, whether you're talking about electrical circuits, LCR circuits, or whether you're talking of finite degree of freedom vibratory systems where you have mass, spring, and dashpots. So in all those cases, whether you have series or whether you have parallel, one will be in that form, the other will be in this form. That's essentially what we are talking of isostrain. Here we are talking of isostress. Now the reason why this is usually much more accurate for EL, whereas this is not so accurate for ET, is because of that those two assumptions that we're talking about, namely the isostress and the isostrain. The isostrain is a little more reliable assumption. That's what happens. It's closer to what happens in reality. Whereas the isostress, there is a slight mismatch, because remember, this is a very crude way of putting the fiber in the matrix. In reality, you saw that the how the cross section looks, right? So this is how it looks. So I can actually take this and do it. I might be a little better off, but what I'm doing is I'm smearing that fiber throughout, and then I'm taking the fiber and the matrix as two laid over each other. Of course, I'm taking the exact same areas, because this will be pi d squared by 4, as we saw yesterday also, and this is, let's say, some cross-sectional dimension A versus A. So you're talking of pi d squared by 4 divided by A squared as the volume fraction of the fiber, and 1 minus that as the volume fraction of the matrix, which is what we are spreading out in this particular way, because it makes it easier, the life easier for us for the derivation. If you're trying to do it in this way, of course you'll have to have a mix of probably polar coordinates and or the Cartesian coordinates, and try to do some few transformations and try to get at that, because at the interface is what you're interested in, how the stress is distributed, etc. It's a little complex. Not that it cannot be done, it can be done, just that it's not worth spending so much time in an introductory course like this. Okay, so which is why if you're looking at once again what we talked about, the Voigt model, which is the upper limit, and the Reuse model, which is the lower limit. The upper limit is usually a little more reliable, the lower limit is not so reliable. So in fact, for the case where ETF and ELF are equal to each other, then what we will actually end up with is, if we were to plot versus volume fraction, the same E for the composite, whether it is ET or EF. So we saw that essentially it's a straight line, that the other one was almost going like this, but in reality, as Ivan said, it will be slightly different, and that's what we end up with, which more refined micromechanics models will give you. What we have looked at in this is the solid lines. Okay, in yesterday's class we derived this line, today's class we have derived the bottom solid line. So that gives you kind of the upper and lower limit. In reality, it lies somewhere in between those two, which is the dashed line that you see over here, right? But remember, I mean, we are talking about two different quantities here. One is the longitudinal modulus of the composite, the other is the transverse modulus of the composite. Longitudinal modulus being usually much larger compared to the transverse modulus. You're just talking about in terms of the philosophies of Voigt and Reuse to get from isostrain and isostress the kind of limits that they're talking about, and eventually to get to what is reality. Okay, so this is ET. So yesterday I showed you how to derive this and asked you to derive this, which is very analogous. So all that you're doing is replace E with nu, the Poisson's ratio, and don't get confused between the nu and the V is another important thing I'm emphasizing once again. And here also, today we derived this. I want you to derive something very similar, which is for the shear modulus. That another very important thing. Okay, so another very important thing that we need to for a lot of the calculations at the mesomechanics and even the macromechanics level are the longitudinal Young's modulus, the transverse Young's modulus, the longitudinal transverse Poisson's ratio, and the shear modulus, which is longitudinal transverse. In fact, there's one more, we will come to that a little later, but right now you see the parallels between EL and ULT on the one hand, and between ET and GLT on the other hand. Okay, here I stressed upon the fact that this is set of two subscripts, and it's very important how you put the subscripts, because one is an input, the other is an output. Okay, so you are applying the stress in the direction of the fiber, which is longitudinal, and you're measuring the strains in both the directions and then taking the ratio, putting a negative sign. That's how we defined ULT yesterday, remember? It's just minus of gamma TT divided by gamma LL under the condition that only sigma LL exists, no other stresses exist. So that's how we define that. So if you were to reverse this nu TL, you'll get a very, very different numerical value. Okay, so be careful that nu LT and nu TL are not equal to each other. On the other hand, these two are equal to each other, GLT and GTL, because what is G? G is the shear modulus, which is essentially a change in the right angle for the shear strain for applied shear stress, unit shear stress. So that change in angle, whether you're measuring from this axis or this axis, it's one and the same. So that's essentially you're talking about, right? So it's the change in the angle that we are interested in for a unit stress, shear stress that we are trying to apply. So therefore GLT and GTL are one and the same. So here it doesn't matter. There's nothing like an input output here. It's just a stress tau LT which is causing strain, which is gamma LT, and you're taking the ratio of that, and that's essentially what you are getting, of course under certain conditions. Okay, no other stresses are being applied, etc. Right now, remember that when we were deriving this ET equation, at each stage I was telling you, not only were we going step by step, but we were also saying what is the verbally, I didn't write it down, but verbally I was telling you exactly what is the assumption that is being made, because of which we can go from step 1 to step 2 and again to step 3, step 4, step 5, etc. At each stage there was something that we had assumed, which I verbally expressed, and that's how we ended up with this and eventually that, right? So I want you to go through a similar process when you explain to me next week about this, how you get to this derivation. At each point mention the assumptions that are invoked. Okay. Yeah, just whatever I just mentioned. So at the point of invocation, or where you're actually accessing or utilizing that assumption, which is what I mean by invocation here, and then of course you have to comment on its validity, how accurate you think it is, why you think it's accurate, or why you think it's very crude, that particular assumption, and just speculate on that, okay, qualitatively. Okay, now this is beyond the scope of your class, but I just wanted to give you a feel of what else we could do probably to improve this whole thing. So we've already been saying that the equivalent homogenized hypothetical material that we have is something that is going to replace the actual material, which is set of two materials, fiber and matrix, with a single material C, which doesn't exist but behaves exactly in same way as this would do in the overall sense, right? Individually within it there's a difference of behaviors, but here we are saying that overall behavior, how much the left and the right edges move, how much the top and the bottom edges move, that will all be the same whether you're considering this or that. Okay, so that's essentially what we are trying to hit at. Okay, but there are a few other things that can interfere. Even if there are only two components in your mixture, fiber and matrix, no additives, still there can be a few other things that can influence this whole thing, and one of them is the heterogeneity itself. Okay, so the heterogeneity that we are talking about here, we have remember that from the actual distribution of different materials, we are going to an equivalent homogenized material, and doing that we are making a lot of crude assumptions. So that heterogeneity actually continues to exist in reality, and that can be taken care of by a factor like beta that is defined over here. There are many ways in which the heterogeneity can be defined, but this is one such way. If you look at the numerator of beta over here, it is defined as the difference between two transverse moduli, the transverse moduli of the fiber and the transverse moduli of the matrix. But of course, the matrix being isotropic, I don't need to put T explicitly over there, right? So it's ETF and ETM, but M being isotropic, I just can write it as EM. What would it be if this were a truly homogeneous? Then your beta will go to 0 because your ETF and EM will be equal to each other, and the other things in the equation will not affect it in any way, right? So you will have beta going to 0, and if beta goes to 0, this expression that we have for the transverse modulus, you can see that the denominator term has a beta over here. If I put beta equal to 0, the term within the bracket just becomes 1. So the denominator vanishes, and what I have here is two terms. There is a beta over here, so the second term will go, and I will just get ET equal to EM, right? It's just same as the matrix, which is the same as ETF, because that's what we started off saying, that these two are equal to each other, therefore beta equal to. So what I'm saying is, if you want to specialize this for a actual homogeneous material, then, or a situation which is kind of impossible, where you're looking near to impossible, which is the matrix and the fiber having same properties, in which case why would you anyway go for that? But if you remember the examples that we talked about carbon epoxy, etc., having 14 times the EL by ET. On the other hand, there were some examples there, like the boron aluminium matrix composite, where the boron fibers were in an aluminum matrix, where it was just 2. So then you see that the difference between the two properties are not so much, then it's closer to being homogeneous than truly heterogeneous, right? So in such a situation, you'll have very low values of beta, and therefore when you have very low values of beta, your ET will become approximately equal to EM, not ETF, because that's essentially, if they're exactly equal to each other, yes, what we just discussed happens. But if EM and ETF are close to each other, that's it's not so heterogeneous after all. Okay, the non-homogeneity this is a measure of the non-homogeneity, and therefore they are reasonably close to each other. Then what happens is that, as I already was mentioning, transverse properties are dominated by the matrix, whereas longitudinal properties are dominated by the fiber. Okay, so that's why ET becomes approximately equal to EM. So when many situations you will find you don't have data, or either it's a proprietary thing because of the industry using that or something, but you still want to make some calculations related to that. You will not go very wrong if you assume the properties in the transverse direction as somewhat close to what the matrix properties itself are, and the longitudinal properties somewhat close to what the fiber properties are, so that you can at least get a qualitative understanding of the trends that are involved, etc., when you have lack of data in terms of the material properties. Now, that's not the only thing this particular model takes care of. The other thing that it takes care of, this L by D. Okay, this abbreviation of L by D we tend to see in various contexts, the lift to drag that we saw, etc. But here we are talking more in terms of the length of the fiber to the diameter of the fiber, right? So L by D, that ratio, we already saw how significant the fiber geometry was. Why did we go for the fiber geometry? We saw that we can approach, as we reduce the fiber's diameter, we can approach almost the theoretical strength or stiffness, which is the cohesive strength or cohesive stiffness between atoms or polymer chains that you have. And since you're able to achieve that, you get very large values for the properties of interest, namely the stiffness and the strength. But in reality, what happens is that this L by D may not be approaching infinity. Okay, it's let's say 10 times, or it's about 5 times. For the typical kind of lengths that we talked about an inch, the diameter is of the order of a few microns. So therefore, what is the ratio that you're looking at? So L by D is reasonably large, and there's no problem. But those are for expensive aerospace applications, primary structures. But for secondary structures, even in aerospace, and sometimes even primary structures in non-aerospace applications, which are more driven by the economics of the problem, then you will end up with something that is what known as a short fiber composite instead of long fiber composites. So when you have short fiber composites, then your L by D will not be that large. It will still remain greater than 1, but not very large compared to 1. So in that case, an L by D correction becomes imperative. So what is that L by D correction that you see over here? You already see in the main equation itself there is an L by D term here, and even beta depends on the L by D over here. This is a secondary dependence and indirect dependence. The more direct dependence is what you see over here. Okay, so let's take that alone for now. Let's say beta is more of a measure of heterogeneity, though it's kind of including the L by D effect also to some extent. The main L by D effect is coming over here. Now if you look at that, you see that as L by D increases, your ET will increase. If keeping everything else the same, if you are increasing your L by D, then you see that ET increases. On the other hand, if you look at this term also, see if you look at L by D over here, you are trying to increase your L by D. It's in the denominator, and it's a positive coefficient, and therefore you will see when L by D increases, beta will decrease. And if beta decreases, you know, once again, because of the way beta is with a minus sign in the denominator and a plus sign in the numerator, this will again have the same effect, that beta goes down, then your ET goes down, right? So keeping that in mind, you're looking at your L by D ratio, the advantage of having a large L by D. If you have large L by D, not only of course your longitudinal properties improve, which is what we saw in a couple of classes earlier, where we saw how the trend is for the fiber modulus versus or fiber strength rather, UTS versus the fiber diameter, right? So that is a huge advantage, but even the transverse properties improve if you have a large L by D because of this particular effect. Okay, so heterogeneity and L by D correction are only two of the things that these two very famous guys, Halpin and Tsai, actually brought into micromechanics. They have written books on this apart from papers, research papers, and whole courses. In fact, 2 or 3 courses can be taught from some of those books with micromechanics alone. Okay, and I put it in a very simplistic form, these two equations. There can be much more complicated versions of these same two equations. Of course, there's only one equation that I've talked about so far, ET. Similar equation exists for GLT as well, but they also take into account the effect of packaging, how tight or loose the packaging is, and a few other aspects as well, which I have not bothered to bring it, because then the equations become too big, complex, and very difficult to see the qualitative behavior like what we just discussed, right? So if you look at the GLT equation also, see here you have a measure of the heterogeneity, because the same quantity GLT, in the case of the matrix, I don't need to specify that because it's isotropic. So it's also, what I really mean is GLTM. Here also I mean GLTM. So we're talking of the GLTs of the two constituents, fiber and matrix. Are they different from each other? Okay, if they are not different from each other, which is homogeneous, then essentially these two terms go to 0, and then you will see that once again there's a matrix domination that happens over there, right? So whereas when this becomes bigger and bigger, this whatever is in the square brackets over here, then you see that that is going to have an effect. Okay, and it's here with a negative sign, here with a positive sign. So in terms of the qualitative sense, increasing or decreasing, it's one similar kind of effect that is there of the heterogeneity over there, right? So that's Halpin and Tsai for you, which is very popular, especially in the industry, aerospace industry. A lot of people use this when they don't have other information about how to get to the composite properties. Let's say they have the fiber and the matrix properties, they typically use more complicated versions of these in order to achieve that. Of course, they don't do it by hand, it's all inbuilt into a lot of the software that they have in-house. They do use these commercial softwares like Abacus, etc., but they have a lot of their in-house subroutines to add to that, and many of these things will be taken care of there. Not only exactly as how Halpin and Tsai has given it, because they also have their own understanding of the problem because of the large data sets that they have created. Based on their own understanding, they have some empirics going into the whole thing, and they empirically modify some of these with some constants, etc., to make it a little more closer to what they observe experimentally in reality, right? Just to say that that's not, Halpin and Tsai were not the only two guys whose works are used extensively. I'm just giving another example of Brintrup, where the effect that we are talking about very different from the two effects that I talked about here, heterogeneity and L by D correction, or even the packaging and etc. But here it's a Poisson's effect. What is this Poisson's effect? Here, if the Poisson's ratio of the matrix were 0, then this is exactly same equation what we had, because if Vm nu m, I should actually write nu LTM, but because I'm taking the matrix to be isotropic, once again I can drop off LT and just write it as nu m, which is the Poisson's ratio of the matrix, and that if that was close to 0, let's say, then what would happen? Your Em prime and Em would be the same. So in other words, Em prime is just a corrected version of Em, okay, the value of the Young's modulus of the matrix. Now this equation is very similar to the equation that we already have, which we derived over there, right, expressed in with, of course, just a Et on the left hand side, taking the reciprocal of that and doing the manipulation which we presented in the previous slide. So this is exactly same, only thing I'm replacing in that equation Em by Em prime, okay, and that Em prime in turn is same as Em except for this correction by the Poisson's ratio. So what is this correction doing? Vm, irrespective of whether it is positive or negative, doesn't matter, most cases it is positive, then you will have the denominator less than 1, and therefore Em is increased slightly, right, to a new value called Em prime. Now that is what is being utilized there. So you will see that once again what we are doing is we are nudging this lower limit a little up through this Poisson's effect. So it's essentially a correction that is happening because of the Poisson's effect. Similarly, all those corrections that we have talked about due to heterogeneity, L by D, etc., will all give you curves which are slightly above this bottom curve that you see over here when you're plotting ET. Similarly, the behavior of GLT also, because both of them have this reciprocal behavior. Yeah. Any questions on this? This is nothing that you need to remember from the point of view of this course. It's just that I just wanted to give a flavor of how it's done. Probably kind of at least slightly better, moving towards what is done in the industry. Not exactly what is done, but it is somewhere intermediate between what we present as the simplest model and what is actually used in the industry.
So what was L and D again? Was D the diameter of the fiber?
L and T?
Yeah.
Yeah. L and D, you mean?
L.
Small L by D? Yeah. So it's like, typically in a composite that you have in the aerospace industry, you will have long fibers, okay? Whereas in the automobile industry, you will have shorter fibers, okay? In either case, there is not a single value because there are so many fibers, each will have a different L value, but more or less diameters will be around the same, okay? Slightly different they will also be. So if you take a sample set and get the L by D measurements of all of them, okay? So then you take the mean of that, okay? So it's totally the average length of a fiber by the average diameter of the fiber that you're using in a particular structural component, okay? So now if that L by D is large, you're truly moving to a fiber, okay? If L by D is very, very small, you're getting into what is known as particulate composites. So instead of fiber reinforced plastics or fiber reinforced composites, you're getting into particulate composites. Now particulate composites are inferior compared to, usually most of the properties if you look at, compared to fiber reinforced composites. Why? Because remember we plotted that versus fiber diameter and we showed that trend, right? Because it approaches as the fiber diameter becomes smaller and smaller. There we are assuming that the length remains a constant in that whatever we showed there. It's actually because of the L by D ratio that it's happening there as well. We are assuming the L doesn't change so much, even if it changes not by orders of magnitude, because remember there we were plotting all the way from atomic distances to let's say 100 microns or so, covering 10 microns in between, which is the more realistic value of most fiber diameters, right? Lengths don't change by that factor. It's a huge factor of 100 or so that we are looking at, right? So it will be some might be an inch, some might be half an inch, etc. So you just changing by a factor of 2 or whatever. It doesn't change the ratio that much. But the fiber diameter has a huge play in this. Lower the fiber diameter, you see larger the L by D ratio, and if larger the L by D ratio, better transverse properties also. We have already seen that huge shoot up in the longitudinal properties. But we are saying that even transverse properties can improve if you are improving your L by D ratio. Why? Because even though the transverse properties are matrix dominated, the fiber has a role, because just like we saw when fiber breaks, the matrix transfers the stresses immediately and makes the fiber effective within a very short distance, and therefore even broken fibers continue to work for us. Same thing here, the opposite works, that if the matrix has a crack, the fiber can help with the stress transfer, and therefore larger L by D ratios are actually useful in improving the transverse properties also, not only the longitudinal properties. Yeah, that clear? Any other questions? Okay. So let's get back to something that we were looking at from a purely a fiber point of view, but we have now known that we can't use fibers by themselves. We have to use fiber along with the matrix. We saw the reasons for that and what is the role that the matrix plays as well. So instead of just talking about carbon fibers alone, boron fibers alone, glass fibers alone, aramid fibers alone, which is of course the chemical name for Kevlar. Kevlar, remember we talked about Kevlar 29 and Kevlar 49. Both of those are actually chemically speaking aramid, just that DuPont has rights over it, the intellectual property rights, IPR, and therefore they call it as Kevlar, but actually chemically speaking it is aramid. Now we talked about each of those fibers, but we know that we can't use fiber by itself, so now we are bringing in a matrix, mostly epoxy, the polymer matrix, thermoset, for lower temperature applications, but also a relatively higher temperature application of a metal matrix composite, which is aluminium over here along with boron. So now you will get more realistic values for composites that are actually in use. There we saw a huge difference between the performance of the fiber and the metallic alloys that they were replacing. You can't replace metallic alloys by fiber alone. You have to replace it with fiber and a matrix. So then, yes, we continue to have an advantage, but not as high an advantage as we saw over there in terms of the ratios of these values, that is the performance index in static stiffness, because the stiffness based design, remember, actually has a square root of E by rho. When you're looking at dynamics, the natural frequency you want to increase, but if you want to just decrease only the deflections, make it less flexible, then E by rho is what you look at, right? Similarly, we saw the strength based criteria, and also I should have probably put E by rho cube, that is a stability based criteria, okay, which we will see much more bigger advantage of composites. So now you will see that yes, these continue to be larger compared to some of the metals, but just that they're not as large as the fiber properties that we had discussed in terms of these material performance indices earlier. So yes, there is an advantage, but not as large an advantage once the matrix comes in. But because the matrix comes in, it does make it a more realistic structure, taking loads in the directions in which the fiber alone was not capable of. Right. So now if you look at these E by rho values, where I've just taken this column values and column values over here, of course this is given in grams per cc, which is also nothing but the relative densities as well, because the density of water is 1 gram per cc or 1000 kilograms per meter cube. So compared to water, what is the density? So you see all of them are greater than 1. So in other words, any of these composites, if you just have a part made only of that composite and it's not hollow, it's just a solid, and then you put it in water, obviously it's going to sink because it has a larger density compared to water, right? Just important to remember for us to understand qualitatively how heavy these are, because we always say composites are lightweight. So you see many of them are about 1.5 times, or at the most, because you're talking of a metal matrix composite, which is not used unless the temperature requirements are large. So most of them are of the order of 1.5, much lesser than 2 usually. There are exceptions, but you are essentially seeing as just about 50% heavier than water of the same volume. So that's something to remember. So taking that along with the values that are given over here, so these are about 2 decades old, these properties that I'm talking about. As I said, there are many different epoxy resins, a whole family of resins of slightly different properties, and huge families of carbon from different manufacturers, from the same manufacturer also, some stressing on strength and therefore sacrificing the stiffness a bit, the Young's modulus a bit, along the longitudinal direction. Others which are more critical on the stiffness, for example, in the boron fibers, we do that because more for space applications where you want the dimensional stability is much more important, rather than the final failure. So when you have something like that, you see that these can actually be a very large range. So that's why we have given some specific fiber names like T300, very commonly used, IM6, AS4, etc. Similarly for the glass also, we have taken a structural glass, S-glass, which is of a particular kind. Again, within S-glass there are many different kinds of S-glasses, which is a S2 glass that we're talking about over here. And similarly, we discussed Kevlar 29, which was inferior in property, Kevlar 49 much better, especially used for a lot of impact energy absorption kind of applications. So you see that Kevlar 49 over there. So once you make that specific, then you also need to make which epoxy you're going to use over here. So these numbers typically give you a specific kind of epoxy by certain manufacturers, and therefore the properties get kind of more or less fixed. Similarly, here also it should have been mentioned exactly which epoxy it is. It's not mentioned from the source from where I have taken it. And this is metal matrix composite, so I need to mention which alloy of aluminium that is actually used. AL2024 is a very commonly used aerospace grade. Since usually the 2000 series and 7000 series which are more often used, you would have studied some of these things in your materials class. So when you use that, these are the properties you get for the Young's modulus and the ultimate tensile strength, and therefore you can arrive at the specific properties of interest. Now you see it goes all the way from 24 for glass epoxy or specific stiffness to as high as 114 over here. So within composites also there's a huge difference that you can have depending upon the specific properties. And as I said, these are all about 20 years old data. So you might have much more improvised values for these, because the material scientists are always looking at ways to improve the fiber, ways to improve the matrix, way to improve the fabrication process of the composite itself in terms of autoclave manufacturing or various other things that are existing, like resin transfer molding or vacuum assisted resin transfer molding, VAR, TM, etc. There are many different ways. And then the structure that is made out of them through hand layup earlier, now through laser guided layup, and there's also a lot of movement from what was the traditional subtractive manufacturing to additive manufacturing, or called 3D printing, etc. So then the properties are going to be varying slightly. So as of now, the kind of technologies which exist, many of the additively manufactured ones, of course they overcome a lot of issues earlier, like the sustainability issues that we used to have. They're much more environmental friendly because you're having only as much material as you need to use. But they also have a disadvantage that some of the properties are not as superior as the properties that you have for the subtractively manufactured, traditionally manufactured composites, right? So here also again you see a wide range, starting from about 566 in, of course, thousands of meters per second squared that you have for the boron aluminium, which is a metal matrix composite, all the way for a carbon fiber epoxy composite about 1845. So you see, depending upon the specific requirements, as I said, the strength, stiffness and stability are all three important requirements, but sometimes one might become the one you're optimizing, you want to maximize. The other two might become constraints. You have to satisfy it, but you don't need to have it much more than whatever is the minimum prescribed level. Okay. So whereas there can also be designs where all three or at least two of them become very critical, then you have to appropriately give a weightage and come up with an objective function which is kind of weighted over those two depending on their relative importance. So now that we have this data from about 20 years ago, we want to get to more latest current data, and that's what your last homework for this week will be all about. So those are, remember, the longitudinal properties. So now the final homework that you will have is about these properties, the same 3 properties like the way I have calculated in the previous slide, but for more current materials, more materials that are better performing. So to put it more specifically, I'm looking at the top 5 fibers that you can lay your hands on through your online searches, the book searches, or there are also material handbooks that you can get from the GT library using your VPN. So if you look at all of those, you can find some of the fibers which have the largest values of these. Of course, they will not give these values. They will give only sigma u values, they will give you rho values, they will give you E values. You have to calculate these ratios and the square root or whatever, or the cube that you see over here. And then you can take the picture after I bring the next, the right column as well. Okay, so find top 5 fibers each which are resulting in an epoxy composite. In other words, you choose 5 fibers for each one of these. Okay, there could be some which are good both in strength and stiffness, some which could be better both with stiffness based design and the buckling based design. That's the stability criteria. But what we are looking at is to see which are kind of the cutting edge fibers that we have today, okay, so that you have an idea of how big an advantage we have with the kind of materials that we are dealing with today. And in spite of that, we have to make geometric choices in terms of the semi-monocoque construction with the beams and the skin that we have for the wings and the fuselage, etc. Right? So what I want you to do is to keep the epoxy fixed. As I said, epoxy is a big family of resins, but we want to keep that fixed because we want to just see the state of the art with the fibers alone, right? So we keep the epoxy the same. We take the volume fraction of the matrix to be 0.4, which means the volume fraction of the fiber is 0.6, 60% fiber, which is kind of typical of most aerospace applications. If you want really good quality primary structures, you go all the way up to about 60% fibers, okay? So maximum values for each of these performance index using, of course, you will find a lot of the FPS units, etc., which are continue to be used extensively in the US, but just to put everything on the same comparison, because you don't want to be comparing apples and oranges, I want you to stick to these 3 sets of SI units that we have already discussed, right? Which come from sigma u and E being in Newton per meter squared and your density being in kilogram per meter cube. Now, any chosen fiber, you should also ensure that, because you're going to end up with an epoxy composite, it should be compatible with epoxy. In other words, there should be a chemical compatibility. They should not be reacting with each other, for example. So it should actually blend with that particular matrix, okay? So don't talk about fibers which are not suitable to be working with epoxy, okay? That you can find out in wherever you get the source of information from. And also, as I said, we don't want to play around too much with the values of the matrix properties itself. So I'm giving you matrix properties like the Young's modulus of the matrix, that is epoxy. Oops. You can take it as 3.4 GPa. Then you can take the Poisson's ratio as 0.3, okay? And you can take the, I'll put up this slide separately, so I don't know why this happened. The line spacing seems to be much lesser than. So then you take the strength to be 600 megapascals, and finally the density. So I'm just giving you the epoxy properties, standard to be used with each of those 15 fibers. 5 for this, 5 for this, 5 for this, 15. But as I said, some fibers might be common across that. So maximum of 15 fibers for the whole team, all 4 of you put together, right? So you can split between yourselves and work on each one of those criteria and or see how you can split the load like you've done with the previous homeworks, right? Then I want you to repeat with the aluminum matrix, okay? Once again, check for the compatibility. Many of these fibers which work with the epoxy can also work with the aluminum matrix. So you might be able to repeat some of those fibers, but some may not be. So then you have to go for a few new fibers, okay? So then you repeat that with aluminum matrix. Once again, I'm giving you the properties for aluminum, which is EM equal to 71 gigapascals. The Poisson's ratio is 0.3. The sigma u is 200 megapascals, and the density is 2700 kilogram per meter cube. And as always, I want you to cite all references at the specific locations where you've got the information and you're utilizing it in your presentations. Okay. So this kind of completes the set of 3 small homeworks that we have, putting them all together. So this is all kind of merged. Let me see if I have it better.
This after derivation.
Yeah, this.
Yeah. There are 2 derivations.
Yeah, you can take a picture of this. I think the line spacing is fine on the slide, but when I'm for some reason when I'm projecting it, they're all getting merged into each other.
There's 1 derivation of the Austin switch and none of the.
Okay, so this I'm done for the class today. If you have any questions, I'll be happy to answer.
Austin is 4.1 and 4.2 is the shear modules.
That's the 3 parts. And when is this due?
Next week, next Monday, if you are ready. Otherwise, you can do it on next Thursday. I think let's do it on Thursday. All 3 of them. So you'll have